So let's continue with the cash flow now. So I'll do a little bit of review on the LPCC, then we'll move into then we'll move into the speech perception part. Okay. So again, anyways, so we'll try it again. Okay, so we'll do a little review on the okay. 还是这个大小声点准，看一下这个会不会好一点？Hello， 好，那我们继续好了。So we'll talk about LPCC model and then LPCC coefficient and then continue on the speech perception. Okay. So anyways, so for the past couple of weeks, right? So about speech analysis, in a way that start by speech production, understanding Chinese domain, frequency domain analysis, now into a linear prediction model, which tells us the filter part, and then move into capsular analysis again, trying to tease apart source and filter through capsular transform. Now we're moving in space that sort of start putting all these tools together to derive, we call it coefficients or features or representations of speech signal that can be, further down user for other speech technology input. Okay, so LPCC is one such feature extraction, or we call it speech features extraction. So here's a complete pipeline for doing LPCC, right? So you have the signal, the speech signal comes in. We'll do a first sample preemphasis that try to amplify the high frequency component. Show time processing happens in this particular blocks, okay, deciding the N and M, okay, number of things to overlap, number of samples within a window, decide which window you want to use so that you make sure, at the edge it has lower distortion. Now this part, basically, think about, right, if you take the window and then, now we start to represent the key information about the signal. You can do, window do time domain phase extraction, or you do spectrum FFTs and then you get a frequency, or you can do LPC, then you get LPC coefficients, okay, or you directly take the spectrum and then do Kestrel, right? So LPCC essentially, I say, okay, we're in a space of trying to represent the features. Let's do an LPC analysis. Okay, the LPC analysis, the inside of that LPC analysis, we know there are two particular methodologies to compute the alpha coefficient. Right? So if we use autocorrelation analysis, just need to decide how many p order you want to look into, how many past samples you want to look into, and then you derive the alpha coefficient. And the LPC models can be converted to capsular coefficients, okay, through this Z inverse transform on the system functions of the LPC model. Then you pick the portions of the signal pick the portions of the capsular coefficient you want. That part we call it parameter weighting, and then eventually, also take temporal derivatives. So every single frame, okay, you go through all these blocks. Okay, to eventually derive a set of representation or features or some inputs, okay, to tell you, so it kind of encode what the most important information about that particular segment of time domain signal. Okay, so this is the whole process. For most of the speech analysis, speech features, it follows very similar process, and then various feature extraction you look into, it basically takes a different approach, maybe in particular different blocks, okay, and then they modify those blocks and advance those blocks to make it better in their particular application. But this overall framing you can keep in mind, okay, so from the speech signal, through some short time, through some spectrum representation, then eventually add a bit of temporal information to represent that particular frame, then move on to the next frame, repeat this process, move on to the next frame, repeat this process, so that you can start deriving all these features. Okay, so we'll talk about the connection between linear prediction analysis and the capsular analysis. Okay, again, repeat. We know the LPC model, right? We think about this. This is the signal spectrum. This is the input or excitation spectrum. The difference between them is the system spectrum, right? Which is the LPC model. That we know is the sum gain divided by 1 minus number of samples in the past, alpha k z sub k, z minus k. We can rewrite this polynomial thing as a rational form of basically products of the poles, okay, pole locations. So capstrom, the capstrom definition is the inverse spectrum transformation of the log of that particular spectrum representation, right? So if your LPC model has this h of z, okay, take the log, tease apart the source and the filter, take the log, make them into summation, and take the ZT transform. Okay, so this is we call LPC capstrom in the capsule representation of the LPC model. Okay. The motivation of using LPC in combination with capsule representation is people do find it more robust compared to using LPC coefficient. Okay. At this point, you can start to see, engineering start to take away. Okay, we start with the speech production, source and filter linear model. Okay, with that knowledge of the speech production, we know how we can derive mathematical formulas to derive things. Like LPC is one particular way to get the filters. Capsule analysis is one particular way to get the filters. Smart engineers start putting things together to say, let's do LPC plus capsule analysis. And empirically, meaning whatever technology they design, usually it's the automatic speech recognition, it's the first technology they tested out. They found it actually works better. Okay. Now, then people don't use LPC as input for recognition task, or they also don't use just the capsule analysis. Okay, they use an LPC capsule coefficient as their input. Okay, but the overall concept is very similar. Okay, between the two, it starts to just really start combining things that we know to be put as a set of feature extraction approaches. Okay, and last time when we talked about capsule analysis, we know if there's a minimum phase signal or minimum phase system representation, okay, you can compute that capstrom coefficient using a recursive formula like this. So again, you can imagine the LPC capstrom coefficient can be computed recursively. Okay, once you derive the AN coefficient from the LPC. AN coefficient are computed using short-time autocorrelation method, where eventually you're computing all those partial correlation plug into a recursive. Also, you compute this each order of the AN coefficient recursively. Once you recursively compute that, then you can recursively compute the LPC capstrom coefficient. Okay, so basically, essentially, if you think about it in C loop, right? So basically, two different C loops that keep doing this recursive C for loop, doing this recursive calculations. So then you can find your alpha hat of n. Okay. All right. So let's continue. So if you want to do a real part, basically just take these two things. Okay. All right. We'll go through one block at a time. Okay. So pre-emphasis, again, speech spectrum has a high frequency roll-off. Okay. So the effect of Caldwell pulse spectrum basically makes the speech wave always has this kind of shape, okay, which originally is okay, but because your computer has finite precision, okay, and think about how many steps we have to go through to be able to compute the features, okay. A lot of these are kind of either multiply or summing or something like that. So those can make the value too small, that's beyond the precision. So this is more of a standard approach. Basically, you boost up the high frequency components, so make sure through this processing that you do, okay, it doesn't lose that final bits of information at the high frequency. So it's very simple. You just apply a typical typical pre-emphasis filter. Basically 1 minus AZ minus 1, A is between 0.9 to 1. It basically boosts up the energy near the pi locations. Provides about 20 to 30 dB high frequency boost. which is okay generally because a lot of speech signal are eventually more or less concentrated on low energy. So you have a little bit boost of the high frequency energy, basically just to make sure it's less susceptible to finite precision effect. Okay, the actual implementation is easy. Okay, so as a signal comes in, take what's the output of the previous signal points times this alpha like design, and minus that becomes the current sample. Okay, by doing this, you're effectively doing a high frequency boost. All right, then LPCC, the part where we have short-term LPC analysis. So basically, you talk about short-term, then you talk about LPC analysis. Okay, right? Short-term, we actually the operation of that is called frame blocking. Take n samples, take m shift, the frame overlap is n minus m samples. So we want to make sure m is always less than n. Okay, when that's happened, is we call the sliding window approach. So the spectrum estimation of this frame usually is smoother. So you can write that as the Lth frame, okay, of the speech is x sub L of n, okay, that equals the original speech signal ml plus n for n from 0 to n minus 1. So there are basically n points within each L frame. Okay. Then you move one, we would move another frame, so like x2 of n, and you basically shift by n, okay, within n there's still n points. Okay, so it's just a compact mathematical notation that tells you the frame and the sliding window of the frame. So that's a simple mathematical notation. The typical length of the window we choose is between 20 to 40 milliseconds with shift about 10 to 20 milliseconds. Okay, so this is empirical. Usually that comes from experiences, and also because we know a little bit of narrow band and wideband analysis. This window band choice decide how big and how width of your main lobe width. This is the proper choice. Okay. For me, I usually see things like more like 40 millisecond and 20 millisecond overlap. If you want to make it smaller, that's okay too. Okay, so 20 to 10 millisecond overlap. So windowing function. Okay, so again, once you frame block it, you get a short segment. Okay, then you use window function to smooth signal at the beginning and ending of the frame. So we call W as a window function. We know that. So your signal, right? The Lth index frame of your signal multiplied by the windowing function. Then you get your windowed short segment out of the original speech sound. Okay. Typical window in use, we use Hamming window function. Right? So again, Hamming window is a simple modification of a rectangular window by multiplying this cosine. So basically, what it does, right, is it shifts the representation to a certain frequency being, so that whatever there's a peak in the rectangular thing, it gets canceled out. So basically it's not a new window. Okay, basically it's a rectangular window. We know there's some peaks that's at the side lobe peak that appears, which we don't like. Okay, how do we cancel that? You move this thing, okay, to there and give it minus sign, and it gives you that. So, but the time domain representation is that. So it's a sort of a Gaussian shape kind of thing, but toward the end it doesn't hit zero. It's sort of close to zero and then jump to zero. Okay, so that's a Hamming window. Very typically used windowing function. If you are in the space of doing pitch extraction, okay, there's some tool that like to use rectangular window better because it has, again, a main lobe width is much smaller. Okay, so you want to get precise pitch or precise velocity within the signal. It may be better to use rectangular window. Otherwise, usually people just use Hamming window. Hamming window, I see much less use for Hamming window, although they have the same effect. Okay? But if you want to have that effect, just use Hamming window, because Hamming window, all the side lobe link are very low, and they're consistently low across all other frequency bands. Okay, now once you have the short segment, once this window is done, then use the Elkin-Su autocorrelation method, okay, to try to compute the coefficient. Right? So you want to compute this short-term autocorrelation function, just that short segment window signal, right? With the short segment window signal with the shift. Okay, that shift depends on the number of orders you choose with the LPC. Okay, just sum it up. Okay, so once you compute all these autocorrelation function from 0 to m, then you have all the values that you need to plug into Lorentz interval recursion. And then you can compute those LPC coefficients. Once you have those LPC coefficients, plug into again recursively the formula for computing LPC capstone, because these are minimum phase system or signal. Okay, then the LPC the capstone coefficient can be computed again recursively as we showed last time. So, and all these things are computed recursively doing LPC, then do a capstone analysis, and then you get a set of coefficients. Okay. All right. So typical numbers of capstone coefficients about 1.5 times the number of order P you choose. Okay. Usually P you take 8 if you're 8 kilohertz. Okay. Again, if you're 16 kilohertz, maybe you have twice of that. If you have more sampling, of course, the sample number will be much bigger. The number of Q approximately 1.5 times that. Again, reason, no particular reason. A lot of these numbers start to be very empirical. Okay, once you pick and choose and seems to work well compared to the other numbers, then it becomes a know-how. Okay, we just choose this particular number of coefficient to be used. Okay, now next concept we talked about last time, which is again, you can start thinking about this. Start to become an engineering approach, right? It has nothing to do with speech production knowledge, right? So for all the time we inspire the computations of feature extraction because we know source and filter model with that LPCC. Okay, now per frame we can extract all these 13 or 12 features. Okay, every frame can extract that to represent that particular frame. Okay, but then when we do that, we're assuming every single frame, okay, they don't have any information with related to each other, okay, which is not quite right. Okay, so what people think is, okay, to properly capture what we call the temporal characteristics, okay, the capture is good at representing the spectrum within that frame, right? Using LPC with capture analysis, you represent the smooth curve of that formal structure within that frame. But how that has been changed across frame, okay? Usually what the people do is basically you do a kind of a temporal first order and second order delta or derivatives. Okay, so you look at a window beginning and end and then see the differences, or we do it twice. Okay, so to be able to compute we call velocity and acceleration of this capstone coefficient over time. Okay, then use that as additional features for that current frame. Okay, so originally you take a frame, compute your capstone coefficient. Then, and they say, okay, I'll look at what my previous frames are and then compute additional differences of my current frame and the previous frame and the second order differences. Using all those differences as also features, okay, as also representation for that particular frame. Now that represent, the first couple coefficient represent the local property, the second set represent, the velocity or the changes. Okay, the third part will represent acceleration. Okay, so this set of features totally together represent a frame of signal to help us represent that particular segment of speech. So this is we call it temporal capture parameter. Like I said, the precise physical meaning is very elusive. Okay, meaning is very much an engineering hack. Okay, so because we don't have a good way of representing how things have changed over time. We just look at a particular segment and compute a good representation of that segment. But we always know the speech signal is not so discretized. Okay, the sound that we're coming out with that time waveform, there's always a connection between neighboring samples or neighboring frames. So we just basically using this dynamic capture in a way to try to represent the temporal progressions of the capture coefficient. Okay, so there's no physical meaning, so we just use it so that we can have a better representation of time. Okay, another thing called parameter weighting or called liftering. Okay, again, it's idea because we know once you get the capture coefficient, the lower order are more sensitive to the spectral slope of higher order capture coefficient sensitive to noise. Again, we want to make sure we pick those segment out so that by not introducing too much additional auxiliary noise or frequency noise when we do picking. Okay, so again, if you get a set of do a capture coefficient transformation, get a set of coefficient, picking a subset, okay, that picking, always remember whenever you pick a segment, you are always multiplying the windowing function. Okay, so in the future, if you do any work in your lab or whatever, right, as long as that's like a signal kind of thing, you should choose a segment. And then choosing a segment, okay, and then do some analysis. You always already change the frequency component. Okay, so that in this case, Kestrel coefficient as well, right? Kestrel coefficient essentially is a pseudo time domain, okay, because you take the spectrum representation, take a log at the inverse spectrum representation. So it's like time domain, but not the real time domain, okay? If you pick a segment, you are applying a windowing function. Now, if you want to look at those segments and its frequency representation, okay, you will add additional auxiliary information. So you want to make sure some of those lifter you design should smooth out the boundaries so that it doesn't include too much of those problems. Okay. So a quick summary on LPCC, and we'll wrap up and continue on to the speech perception. Per frame, okay, usually, length is about 20 to 40 millisecond, sliding half of that we call it 50% overlap. So with a sliding of 10 to 20 millisecond, every single frame we have about 8 to 14 Kestrel coefficient. It depends on your application, okay, and whatever the choice you use that make your application works the best. You always include a first order delta or second order delta. So the usual practice, you take one, because the first coefficient is always about the energy, okay, of the entire signal. Take again 12, say you take 12 Kestrel coefficient, you take 12 first order delta, second order delta, and you have 37 features. Okay, so it's a very classical number of features you see in many speech-based applications. So usually you see somewhere around basically 36, 39, somewhere around this 40 something. Okay, so usually it's around this range where people take sets of features, okay, to represent per frame if they are in the space of using Kestrel analysis as a way to represent a feature. Okay, that's usually you'll see this kind of number. Okay, later, when we learn automatic speech recognition system, we'll see again if you use a toolbox, okay, the feature that extracts about 39 features. Okay, that's because of this first order delta, second order delta, and the Kestrel coefficient they're computing. Okay, so again, so that's the summary of LPCC. Let's move on. Okay, so we kind of wrap up the speech production. Majority of the speech analysis tool. Okay, the last bit of speech analysis I will talk about is some basic knowledge of speech perception. Okay, then we'll introduce another set of coefficients called MFCC coefficients. Then basically that wraps up the entire speech analysis segment. Then we'll switch gear. Okay, move into more machine learning problem. Here is a lot of it this DSP thing. The second part will be more machine learning issue. Okay, so but that's again. We know how we produce a speech. We want to talk about how we perceiving how we hear those speech, right? The speech, as I talk to you, okay, now you're hearing me, okay, because there's all these mic speakers and me speaking out, okay, it's pumping out waveforms, okay, into your ears, okay, your ear collect this waveform, processes it, send it to your brain, and you start to realize everything, okay. So speech production is, we have to say something, move our muscle, change it, okay, set it out, it has this wave, okay, then I set it out. The waves can be collected by your ears. The ears you have called external ear, middle ear, and inner ear. These are the anatomy of the ear. Okay. So you can imagine fairly easily, we'll show that as well. The sound waveform, your ear has this particular structure. What does it do? It basically collects the waveform, right? It collects the waveform and try to start, let's think about it. These are waveform that's coming in and start to resonate within this middle ear. Okay, as it hits this, we call it middle ear bones. Okay, it creates an impedance and then create additional resonance that go into your cochlea. And the cochlea is where all your nerves about your hearing cells are inside here. Okay, so this waveform creates impedance. Okay, this bone will move. The moves change the emotional energy. Okay, then touches the nerves. The nerves can be in touch, it fires, so it sends electrical signal to your brain, okay? And the rest of your brain take care of it. Okay, so think about this process, right? Ear your waveform and seeing is some oscillating waveform that hits your ear, collecting through this tunnel, okay, hitting some ear bones, and then go into your cochlea. And then this is again a bigger, larger big picture, right? This is your ear outside, and here where we start collecting, collecting sound through the ears. And you have three different, middle ear bones that create some impedance to match. Okay, the thing that it moves, matches the sort of standing waveforms frequency. Okay, creates this resonance, and then hitting inside this cochlea. Okay, and the cochlea will, again, inside will show that it has some nerves, and it actually sends out electrical signals. Okay. So with outer ear, okay, we have pinna, auditory canal, eardrum, okay, basically those kind of stuff. Middle ears, we have three different bones, okay, hammer-radial stirrup, okay, again, it provides impedance matching to the inner ear to ensure efficient transfer between 500 and 4,000 hertz, okay. Carefully designed our, again, human organic physical properties, okay, because our human speech, okay, most of the things are well below, 500 to 4,000 hertz, okay, that's where we start understanding the world. Everybody speaks in this particular hertz, okay, and also that's why when we design the first local landline, right, wired phone, right, pick up the phone and talk on the phone, not the cell phone, the pick on the phone, that thing is 8 kilohertz sampling rate, right, so that's why it's Nyquist rate at 4 hertz, 4,000 hertz. Again, similarly, the whole design of that is because somehow we know how we human perceive stuff. Okay, so our middle ear provides, so this bones provides impedance matching to make sure the energy between the 500 to 4,000 hertz are properly transferred. Inner ear, the things we call the cochlea. Okay, it's a fluid-filled chamber. Okay, partitioned by a basilar membrane. We'll show a picture of that. And then it's kind of wrapped around with auditory nerves. Okay, and basilar membrane is characterized by a set of frequency response at different points along membrane. Okay, we call them Bingo filters. Okay, so this inner hair cell distributed along the basilar membrane, converting mechanical motion to neural activity. Okay, so there are about 30,000 nerve filter banks linked to the inner hair cell to auditory nerves. Okay, so about 3,500 hair cells, 40 hairs per cell is about 20 neurons per hair. Okay, so what's happening here? I'll show the picture. This is what's inside, okay, the cochlea. So it's like this string shape, a membrane, okay. And this thing is actual physical property. It's gonna, because of the stiffness, okay, along this membrane, because of the stiffness, it's gonna move, okay, when there's a certain frequency, okay, within the signal that you actually perceive, okay. So because of the stiffness, so the thing can create resonance. So only parts of it will go up, okay. If you have, around 4.4 kilohertz, all these things will move, okay. And as these things moves, okay, their hair cells around it, okay, and the hair cells will bend, okay, and that hair cell bend and will touch your inner hair nerves, that hearing nerves, and the hearing nerves, as it touches more, okay, it creates more activity, neural activity, and that neural activity sends electrical signal to your brain, okay. So we can kind of imagine, okay, what we're seeing, okay, right? So at the high frequency, this way, low frequency, it can't quite see, we can see this is actually picking up, okay. Low frequency, this part picking it up. So it depends on the frequency within your signal that's being collected, okay, within your ear, as they do the impedance matching. So making sure from 400 hertz to 500 hertz to 4,000 hertz are properly transferred. And then within here, as it goes into here, then this membrane will move, okay, according to the actual frequency within the signal that you hear. Again, all these things are dynamically happen, okay, as you hear stuff, okay, and all these things sends electrical signal then to your ear. So what we're seeing is this on a very simplified level. You can imagine this ear, okay, our ear is a nice sort of a device that matches the frequency component within the signal that it hears, okay, and turn that signal, originally is a wave, okay, to this kind of impedance matching to this thing movement, motional movement. Okay. The motional movement eventually changes to neural electrical activities. Okay, so we take signals, okay, which is waves, right? And so it's wave traveling in this space, right? Because there's air, so my thing travels through your ear. My ear provides good impedance to the wave that comes in. Okay, that waves comes in, hit my cochlear, then the cochlear membrane start to move. That movement will touches my nerves. The nerves being touched more, that creates different electrical energy. Okay, electricity activity is sent to our brain. And that's properly how our ear is working. You can imagine it is a very nice, sophisticated way of doing frequency analyzer. Right? It's a sort of organ or a device that's trying to understand what are the set of frequency component within the signal that I hear. And all these things will convert to different neural activity, and somehow our brain be able to process all those filtered electricity in neural activities and turn it into the thing that we understand. Okay, so basically it's that process. Okay, pretty sophisticated. I think I never before I take this class, okay. Our ear is capable of doing this kind of very fancy sort of frequency matching, and then eventually a lot of engineering tools or speech analysis tools are built based on this concept. Okay, because we know our ears at the particular part are responsible for a certain frequency, and that's the whole purpose. Okay, now we can think about this engineering model here, like we talk about some engineering functions that we use in speech production study. There's also engineering functions or engineering models people use it to understand hearing or speech perception. Okay, it's a transduction to acoustic signal, or more broadly we call it acoustic waveform, to neural nerve activities. Okay. The mass and the stiffness of the basilar membrane varies along the cochlea. Okay, every location x of I along the basilar membrane tuned to specific frequency. Okay, it vibrates with high amplitude. Okay, as it hits. Okay, frequency response of the basilar membrane can be modeled by, imagine like a bank of bandpass filter. Right, so a certain frequency, okay, a particular XI location of my membrane is gonna oscillate. Right, it's gonna vary with the amplitude because of my frequency within my standing wave signal, and then it moves. Okay, so you can imagine that basilar membrane is a set of bandpass filter. Okay, each of them has a critical sort of center frequency, and also the band pass width. Okay, that is actually tuned to it. Okay, so imagine them as a band pass filter. Vibration at location xi. Can you imagine there's a impulse response? Okay, h of I of t. The impulse response of the band pass filter. So S I of t equals the st convolving with the actual impulse response of the band pass filter that we try to model our cochlear membrane. Okay. So vibration of the basilar membrane, okay, transduced by bending of hair cells. So hair cell then detects motion of membrane in only one direction. We call it half-wave rectification. Okay. Y I of t, okay, because these are the amplitude, right? The amplitude variation at each of the location xi. When it goes up, it bends the hair. Okay, so there's only one way of doing things. Okay, based on the hair cell innervated with the peripheral understrate nerves, they tend to fire quite a bit when the hair bends, right? So the thing moves, the hair bends, the nerves are inside of those hair. Okay, so as my hair moves more, the thing touches more. Okay, the nerves within it touches more, then it sends more electrical signal. Okay, so that's basically how the operation happens. Okay, so that RT and WI because average fire rate nerves at location xi along the cochlea. Fire rate increases monotonically, but not linearly with the amplitude of the hair bending. So the hair bends more. Okay, that means there's more energy. Okay, the impulse response there's more. Then it creates more. Okay, firing. Okay, so if there's a certain frequency is a lot, okay, then it bends a lot, and then you hear that frequency more. Okay, so that's basically what your hair cell trying to do. Okay, approximately but not linearly, okay, approximately to the power law relationship, so the firing rate to the yi of t. Okay, having that kind of thing in mind, okay, that's our hearing mechanism, okay. Because of that hearing mechanism, there is a perception study understanding, okay, not how our ears process the signal, as though it's more like because of our ear process the signal that way, when we ask you how you perceive the sound you hear, okay, they're different. Okay, so I'll talk about what that means. Okay, so first, usually people use the center frequency of the cochlear to perform speech analysis because it's our bandpass filter, right? So basically, each of the xi can be responsible for a certain band of the frequency. So then people start to design different scale of the frequency. Okay. So one way we call it Bark scale. Okay. Motivation is consider you have an acoustic signal. You have a standing waveforms. Okay. It's a sum of two pure tones: A1 cosine 2 pi f1t, A2 cosine 2 pi ft. Okay. If f1 and f2 come very close, right? And then what that means is within your cochlear, it's going to be processed by about the same xi. The same bandpass filter will process these two signals. Okay. So if f1 and f2 they get within the same bandpass filter, the firing rate, okay, is a1 plus a2 to the alpha. Okay. If not, they get processed by different bandpass filter, which is a1 alpha plus a2 alpha greater than the original a1 plus a2 alpha. So what that means, if you have these two tones, okay, if they're far apart enough, the overall sound will hear larger. Okay, if these two gets closer, okay, they'll be processed by the same sets of sections of the membrane. The overall sound will sound lower. Okay, so we need to design a scale that reflects that. Okay, so it's basically how the two frequency whether they're being processed by the same bandpass filter or a different bandpass filter. Okay. So that's the concept of designing Bark scale is that. Okay, and repeat. Understand the hearing mechanism, right? Standing waveform that comes in, okay, collects the waveform, bounce create impedance. Okay, the impedance create motion. Okay, motion that comes in, and then basically your membrane has an impulse response that's like a bandpass filter responding to this standing waveform. Okay, as it responds, that membrane gonna move. Okay, as it bends, okay, as it moves, it bends the hair cells around it. Okay, the hair cells within them are a lot of neural hearing nerves. Okay, then because they're interlinked, as it bends more, okay, it fires more. Okay, so and it fires more, it hears louder. Okay, so basically that's an idea. So because of that mechanism, when we ask a person, if I give you a two tone of sound, okay, with individual frequencies, okay, if these two frequencies are too close, they're going to be processed by the same bandpass filter. If they're not, they're going to be processed by two different filters. And when you have single bandpass filter process them, okay, it's A1 plus A2 following some power law, versus two different bandpass filter, okay, processing them, okay. This overall firing rate, okay, between these two different bandpass filter will be summing up will be bigger than this one, makes this sound louder, okay, even though they are the same thing. Okay, so that's what I was saying. It's because only you're changing how F1 and F2. The energy within the signal is the same, but it's simply because F1 and F2 are a little bit further apart, the signal sounds louder to you. Okay, now remember back when we try to compute short time energy, we say that corresponds to roughly how loud it is. Okay, now we have to really rethink about what do we mean by loudness, right? So loudness is a perceptual measure, meaning I ask you, do you think this is loud or not loud? Energy is an objective single number, okay, and I compute this energy, it is a number. Okay, that energy is a number, but because F1 and F2, the difference between the two are, okay, if I change F1 and F2, the difference between them, the way you perceive this same energy signal will make one of them think it's louder than the other one. Okay, so the perceptual scale may not be the same scale as you are looking at the signal itself. Okay, so that's the key point I want to really stress. Okay, so when we talk about perceptual scale, okay, the perceptual scale is how, because of our working mechanism of our ear, okay, that makes us think we respond differently to the same, supposedly same energy signal. Okay, in this case, this is by shifting how F1 and F2 are similar or not similar with each other. You make it sound, seems like we don't change A1 and A2, so energy is the same. We only change the frequency differences between them, and you will automatically hear things either louder or not, or not louder, okay, quieter. Okay, so this is the trick. Okay, and then just on the side note, a lot of speech coding, some of the speech generation, a lot of those techniques plays a trick on speech perception. Okay, there are things that we know humans are susceptible to. Okay, there's things that we know can manipulate. Human can only hear certain things, so they can hide information there so that it's good. Okay, so because the perception of your mind is not the same thing as, it's not the identical thing as you actually measure in that acoustic signal. That's the only thing I want to make sure it comes across to you. Okay, so the distance between F1 and F2, which the sound begins to sound louder, that basically we call the critical bandwidth of the bandpass filter we design, right? Because by changing F1 and F2, the difference between them, okay, we're effectively say I'm using this bandpass filter or this bandpass filter. So that gives us F1, F2 gives us the critical bandwidth for that center frequency bandpass filter. Okay, so frequency scale given by critical bandwidth, that particular scale we call it BARC scale. Okay, so BARC scale 1 to 26 scale. BARC scale number 1 means you have in the original linear hertz, the center frequency is 50, cutoff frequency is 20, the bandwidth is about 80 hertz. Okay, and 50 and 100, and bandwidth is about 80 hertz. Okay, the second BARC scale, 150, 200, and the bandwidth is 100. Okay, and then as it goes on along, the higher frequency, say here. Okay. The 17th, okay, this is 30, center frequency at 34, cutoff frequency at 37, with a bandpass bandwidth 450 hertz. Okay, so again, you can look at this scale. They are not linear in scale. Okay, the cutoff frequency and the bandwidth, they are also non-linear. Okay, this is purely by experimentation. Okay, by changing F1 and F2. Okay, and try to understand, okay, how at what point you start to think the sound sounds louder. That means you are using another location of your membrane to start process this signal that you hear. Okay, so by finding a sense of bandwidth of the F1 and F2 for those signal, you always think they sound the same loudness. Okay, then that means you are using the same sections of your membrane to process that part of the signal, and that's a critical bandwidth for a particular BARC. Okay, so again, the BARC, then this BARC idea becomes a scale. So the BARC scale is basically a frequency scale given by critical bandwidth. Okay, that's called BARC scale. Okay. We'll talk about later. Now there's another perceptual scale called Mel scale. Okay, so these are perceptual scale. Okay, it's a way that we can tell, okay, how we human really listens, okay, to the signal because of how our inner ear works in processing them as some set of bandpass filter. Okay. All right. So we'll talk about that later as well. So again, here we can also say there's an equal loudness contour, right? So here's a sound pressure level, the actual thing that we can produce, right? How loud we can produce a sound. Okay. Here's a frequency. This is a actual frequency. Okay, and along this line, okay, if you ask a particular person, okay, they will tell you they all sound the same loudness. Okay, so again, at 200 hertz, if your sound pressure is about 40 dB, okay, that loudness is the same thing as if you produce a signal at 50 hertz, okay, but with a pressure of 70 dB. These two signals will sound the same loudness to your ear. Okay, so these are equal loudness curve. So loudness, so when somebody, if you after this course, right, when somebody tells you energy, how loud it is the same thing as the energy. Energy of signal is actually incorrect. Loudness, this word is actually as a perceptual word. Okay, all this part, right? If you compute energy, this should be a horizontal line, right? So, but not. Okay, so this line, okay, is a constant energy, but it'll create a different loudness in your ear. So when you say somebody hears louder, it may not because they speak with more effort. Maybe just because they speak with higher frequency, right? So you always think girls or females, they somewhat sound louder. Okay, that doesn't mean they speak more effort. Okay, it doesn't mean the pressures that's being output from their mouth is more. This is because how the ear processes the signal, so it makes it sounds louder. Okay, so loudness is a perceptual scale. It's not a production scale. Okay, it's also not a signal scale. Okay, so all this is need to keep in mind. Okay, so understand this Borg scale from a perception perspective because of the hearing. All right, so again, we know all those xi. How do we know how many bandpass filter, how many frequency? Borg scale is one way to do things. Or also, we also can look back, to experimentally determine the relationship between the location xi on the basilar membrane and the filters in the frequency wi, right? So if you look at the Borg scale, there's a center frequencies, right? So we can look at, and then there's a cutoff frequency and there's a bandpass filter. And we look at, where those center frequency, when we have the center frequency, where in the location of that membrane, exactly this. So what people have studied is by studying the response of the basilar membrane to the sinusoids of different frequencies, people do find, frequency spacing, if you use Borg, frequency spacing, one Borg, right, there are 26 when I show the results, right? One Borg is about 1.2 millimeters along the basilar membrane, Coq usually they're around 32 millimeters. So that relates to about 26 filters. Okay, so again, that's the key. If you ever, do MFCC computation with a male filter, you say you design 26 male filter, the idea is because of this. Okay, male filter, then you do capsular coefficient. And the idea is because of the cochlear membrane is of this particular length. You will find that one particular Borg scale is about 1.2 millimeters along the basilar membrane. That means about 1.2 millimeters, it has a new bandpass response. It has a new bandpass response. Okay, so we can then separate this physical properties of our basilar membrane into a set of discrete bandpass filters. Can you imagine that way? Okay. We'll talk about one thing here and then we'll stop. Okay. There's also a masking effect. So every filter, they're not in isolation. Okay, so you have a critical bandwidth. So every two sets of subsequent filter, they actually do overlap. Okay. So there's also a masking effect. So you can look at this kind of. So every they're not purely separated, and as it goes over here, it doesn't lose. It doesn't mean that when you have a signal here, nothing responded here. Okay, there's always also some small response in a low frequency basilar membrane. This is the actual frequency response curve of a cat. Okay, so if you look at this, I mean, it looks a bit like humans, but as it gets to higher frequency, yes, it works more for a high frequency, but it doesn't mean everything dies down. Okay, everything dies down, but usually you get masked by this kind of idea. So remember this. We'll use this kind of idea to design the male filter bank kind of a thing. Okay, so basically our ears, when we have that frequency response, that frequency response is this shape. Okay, and this shape overlaps. Okay, across 26 filters around your in your cochlea around those membrane location, and each one of the center frequency correspond to each one Borg scale. if you look at the bar scale, okay, how do people define that? It's defined by finding the width of the bandpass filter such that I ask you, okay, do you think this sound louder? Do you think it sound louder? Do you think it sound louder? Until the point you say, okay, hey, I think it sound louder. Then move on to the next bar. Okay, so again, this is a perceptual scale, and it's really quite interesting. So the thing you hear is never really the thing you see, right? The thing is actually in the signal. Okay, so we also have to understand that as well. When I produce this as speech signal, speech production, pumping out air here, now going through your ear. Okay, the ear is a set of bandpass filter, and we responded differently to those bandpass filter, and then your brain process. So it's not exactly the same as we directly compute on the signal. So we have to take another scale of looking at the same signal to be able to say process those signals in a way like human listens to those signals. Okay, so all the previous work we talked about, imagine the way we human produce a signal to take and use tools to process those signal deriving features. Now we're moving to the space to take those signals and say let's find tools to process those signals as though it's like human listening to those signals. Okay, so that's basically from speech perception. Okay, now we'll stop here. 那我们下次再继续讲 MCC。